This Calc 2 lecture is the second part of 2 of graphing polar equations. In the previous lecture, we graphed everything above here from page 1 of your notes. This lecture, we will learn how to graph these. We are going to be graphing limaçons and roses. There are 3 types of limaçons. These next 2 pictures are from the PowerPoint that is included up on Canvas. There are 3 types of limaçons. A cardioid, which is heart-shaped. A limaçon with an inner loop. My drawings are not so hot. You'll see better ones in a minute. And a limaçon with a slight indentation. Sometimes they are called dimpled limaçons. They remind me of butter beans. Don't know if you have ever seen a butter bean, but that's what these things remind me of. So, better examples. A limaçon with an inner loop. You see the inner loop right here. A limaçon with a slight indentation. You see that right there. A cardioid. You see that right there. Now, a little bit of vocabulary and a couple of observations. First of all, the cardioid always has the pointy little part of the heart at the pole. A limaçon with a slight indentation that's dimpled that reminds me of a butter bean. So there, that thing reminds me of a butter bean. You will never have anything at the pole. There is no coordinate right there. A limaçon with an inner loop does have a point at the pole. You need to be familiar with 2 vocabulary words, the word bulk and the word wings. The bulk of a limaçon is the big part of it. In all these instances, it's in quadrants 1 and 4 in these particular examples. But the bulk is what you see that is the major part of your limaçon. Your wings are these little things. Right there. So 3 different types of limaçons. You should be familiar with the vocabulary of bulk and wings. So now let's start graphing. Again, if you do not have that summary of your polar graphing out, you might want to get that out to help you a little bit. So we are starting with the graph of r equals 2 minus 2 sine theta. First of all, limaçons will have 2 numbers here and here with a plus or a minus sign here. This could also be written like this, factored out, so you have 2 times the quantity 1 minus sine theta. These numbers right here are A and B. You know that you have a cardioid when the absolute value of those things are the same. A cardioid has those two numbers, their absolute values are the same, then you know that you have a cardioid. Now, let's review for your trig one more time where your trig functions are positive. All of them, sine positive here, tangent positive here, cosine positive here. Let's rewrite this equation, 2 minus 2 sine theta. And you are looking at sine theta, in other words, which trig function you have, and whether this value is positive or negative to determine where your bulk is. So our bulk will be in the quadrants where the sign is negative. So therefore we know that that will be quadrants 3 and quadrants 4. To figure out where the back of the bulk is, and let's go back to this picture a second. The back of the bulk, here's the back of the bulk right here. Here it is, and here it is. To figure out where the back of the bulk is, we need to add those absolute values together. So 2 plus 2 is 4. So in quadrants 3 and 4, this is where my bulk is going to be. To figure out how far back I need to come, I am going to add their absolute values. So this particular graph, the back of my bulk will be at 4. 1, 2, 3, 4. So there is the back of my bulk. Your A value, that absolute value, is your wing length. So my wings, all right, this is a cardioid, so I'm just going to sketch. It's not going to be right, but I'll at least give you an idea. It's supposed to look something like this. But my wing length is supposed to be the absolute value of A, so in this instance, it's going to be 2. Here's A. So my figure has wings that come out to here, and 1, 2 this way, right here. So again, I could make a rough sketch right now. Remember, it's a cardioid, so we are going to have a point at the pole. So it's going to look something like that. Okay? Not perfect, but at least I have a general idea of what this thing is going to look like. Now, if I want, all right, do you see how this one I've drawn just it's a little bit higher and this one's a little bit lower? If I want to make my shape of my wings a little more accurate, or the shape of my bulk a little more accurate, I could pick values for theta and figure out, for instance, what those values would be. So for instance, I could pick 30 degrees or pi over 6 for theta, and when I plug that in, up here into my equation, I would get out that r is equal to 1. So I know, so let's wait and let's make this thing a little more accurate. So there's that point, there's that point. Here's 30 degrees, and there's 1. So I know that the point that will be symmetrical to that is right there. So I can now draw my wings very, very accurately. I could do the same thing with the bulk by using, for example, 210 degrees. That would be a 30-degree reference angle in quadrant 3. So that would be right here. And when I plug in 210 degrees, I get out 3. So that would give me that point right there. And using symmetry, I just think about going around this way. So that would be right there. So I can now draw this shape. Oh, that was my eraser. Shoot. Pretty accurately. Guys, when you sketch these, I'm not going to ask you to find those other points. You only need those if you are trying to draw super, super, super accurately. All right, let's look at our next equation. So flip back to page 1 of your lecture notes, and you will see that that equation is 3 plus cosine theta. R is equal to 3 plus cosine theta. Please notice that you can't factor anything out of these two terms, and that there is an understood 1 right there. This is also a Lie Mason because it's in that pattern of a plus or minus some number times sine or cosine of theta. Guys, when A's absolute value is bigger than B's absolute value, then you have a Lie Mason with a slight indentation. You may call it a Lie Mason with a slight indentation. You may call it a Lie Mason with a dimple. Doesn't matter to me what language you use. I just need to know that you know that it doesn't have an inner loop and it's not a cardioid. So let's look at our cosine is positive. So that tells me that my bulk is in quadrants 1 and 4, because that's where cosine is positive. I know that the back of the bulk is 4, because that's the absolute value of 3 plus the absolute value of 1. So this thing is going to be in this region. It's going to have some kind of dimple like that. The back of the bulk has to be over here, and it will need to be at 4. So let's erase and see if we can do this a little more accurately. 1, 2, 3, 4. There's the back of my bulk. Remember that your wing length is 3. 1, 2, 3. 1, 2, 3. So I know that this thing is going to look approximately like that. Drawing's not real good there. Let's see if I can make that a little more accurate. It's easier on a sheet of paper when you can rotate it. So now the last thing that I need to do is to find my indentation or my dimple. Guys, instead of adding the absolute values like you do to find the back of the bulk, you subtract the absolute values to find the indentation. And that is going to be away from the bulk on the pole. So we're talking in this direction, away from the bulk and away from the pole. So when I sketch this, I need 1, 2. All right, so this thing is going to look approximately like that. Our last limaçon has the equation 2 plus 3 cosine theta. You should be better now about telling me where the back of the bulk is, just right off the bat. So the back of the bulk is going to be 5, and it's going to be in quadrants. Okay, guys, where is cosine positive? So quadrants 1 and 4. All right, here we go. 1, 2, 3, 4, 5. All right, there's the back of my bulk. My wing length is 2. 1, 2, 1, 2. So already I know that this thing in general is going to look like that. Again, not a beautiful drawing. You could find some additional points to help you make your bulk a little more accurate. Now, we have an inner loop. So, does my inner loop look like this, where it's teeny tiny, or does it look like this, where it's humongous? Let's figure out how to do that. My inner loop. I take my absolute values of my two numbers, but I subtract them. And then I take the absolute value of that result. So I'm going to get the absolute value of 2 minus 3, which is -1, and that absolute value is 1. So my inner loop goes inside, so this direction, inside, and the number of units is 1. So it's a teeny tiny little inner loop in there. Last thing I'm going to graph for you guys are roses. Roses look like flowers, and flowers have petals. In general, they look like this. R equals some number, sign, all right, let's try this again. Let's just do it at the bottom. R equals A cosine n times theta, or R equals A sine n times theta. So we are graphing R equals 2 cosine 2 theta. So the first thing I notice is that this number is a 2. And if you're thinking, hey, Is this a lemniscate? The answer is no, because it doesn't have a square up there. If that's a square, you have a lemniscate. Not a square, so not a lemniscate. So we have a rose. First thing that I want you guys to learn about is the axis of symmetry for our petals. Just like a lemniscate, if this thing is a cosine, your axis of symmetry is going to be 0 degrees or 0 radians. So I am going to have, and I am not drawing it all the way across, I'm just drawing it in the positive direction for the pole, and you'll see why when I draw the second graph. Now, your flower has a certain number of petals. If n is even, the number of petals will be 2n. If n is odd, the number of petals will just equal n. So n here is even. So I know that I am going to have 2 times 2 or 4 petals. So the first thing that I want to do now, after I know my number of petals, is situate them accurately on my polar graph. I have 4 petals within this whole 360 degrees, or within this whole 2 pi rotation. So I need the axis of symmetry of a petal to be 90 degrees away from the last one. So I know that the next axis of symmetry will be here at 90. The next one will be at 90 plus 180. 90 plus 90, which is 180. The next will be at 180 plus 90, which is 270. So in general, my rose is going to look something like that. All right, to figure out my petal length, just like a lemniscate, this number right here, let's put a different color in here. That right there tells me my petal length. It's the absolute value of A. So each one of these petals is going to be 2 units long. When you draw your petals, they don't overlap each other at all. So in other words, it doesn't do this. See how I have those overlapping each other? It doesn't do that. Your petals will more accurately look like that. So let's draw this 4-petaled rose over here. So there's the graph of 2 cosine 2 theta. All right, our next graph and our last graph is the graph of r equals 4 sine 3 theta. This is also a rose. Let's talk about the axis of symmetry. When you have sine of some angle measure, your axis of symmetry will be 90 divided by n. Remember, this number here, that's n. So in this particular instance, my axis of symmetry will be 90 divided by 3, or 30 degrees. So my first axis of symmetry is going to be here at 30 degrees. Now let's figure out how far apart they need to be. Again, I need to have 3 petals. So I'm taking the whole 360 degrees, or the whole 2 pi rotation, and I am dividing that by 3. So I'm going to need my next axis of symmetry to be 120 degrees away from 30. So in other words, 120 plus 30, or my next axis of symmetry, will be at 150, which is right here. The next one will be 150 plus 120, or 270, which will be right here. And hopefully, visually, you can see that therefore my 3 petals are distributed the same distance apart on my polar graph. Please remember that the petal length is 4. 1, 2, 3, 4. So go around, that would be here. Keep on going around, that would be here. So if I am going to relatively accurately sketch these petals, they would look like that. Now, you may be thinking, oh, these are just nice, pretty little graphs. They're never used in real life. Not true. Ask your chemistry instructor what kind of particle follows the path of a lemniscate, because there is one. I don't know enough chemistry to be able to tell you. I can't tell you the difference between a proton or an electron or an ion or an atom, but I can tell you the math behind that, though there is something that travels the path of a lemniscate. Okay, so far what we have done for polar graphing, if you had a good pre-calc teacher, you know every single bit of what I have discussed so far. The last thing that we need to talk about in this particular section on graphing polar equations is to figure out the points of intersection of pairs of these polar graphs, because we are going to, in the next section, begin learning how to find area within these. For example, overlap a circle and a lemniscate and tell me the area of the intersection of those two things. So we need to be able to find points of intersection. So let's say that I have the following 2 equations. Do you guys recognize that those are both cardioids because A and B are both the same value when you look at their absolute values? So to be able to find the points of intersection, you are going to most often use the idea of setting these two things equal to each other, because you have r and r, so therefore you can set 1 plus sine theta and 1 minus sine theta equal to each other. Subtracting 1 from both sides of the equation gives you sine theta equals negative sine theta. Adding a sine theta to both sides gives you 2 sine theta. Dividing both sides by 0 gives you this equation. Hopefully you are aware that within one rotation, within 2 pi, because that's all we're talking about on our graph, that the arc sine of 0 is 0 radians or pi radians. And once you have what theta is, you can plug both of those values back into either one of your equations and find r. So I just picked this first equation over here. I picked this one. Here it is. I plugged in 0 radians first. Sine of 0 is 0, so I got r is equal to 1. So when theta is 0 radians, r is 1. I repeated the process when theta is pi. Sine of pi is also 0, so r is also 1. So when theta is pi, r is also 1. So these are the two intersection points for these two cardioids here and here. And you'll see that I actually have drawn quick sketches of both of those. And I can see the points of intersection right here and right here. And you're going to need those desperately in section 11.5. Now, one other point to make to you guys. Yes, they're cardioids, so they both intersect right there, but that point at the pole is not going to be useful to us at all. Let's do one more of these. Find the intersection points of this circle. That's a circle tangent to the pole. And this equation here, which is a cardioid. So both of these are equal to r, so I can set these two things equal to each other, which I have done here. I added cosine theta to both sides, which gave me 2 cosine theta on the left. I then divided both sides by 2 and got cosine theta equals 1/2. Again, within one rotation, 0 to 360 degrees, or 0 radians to 2 pi radians, you are trying to find where the cosine of the angle is equal to 1/2. So arc cosine of 1/2 equals. If you do this on your calculator, you will get pi over 3. But there is another location where that happens at 5 pi over 3. Because you know that cosine is positive in quadrants 1 and 4, and that a 30-degree reference angle in quadrant 1 would be a 30-degree reference angle in quadrant 4. And so therefore the 60-degree, let's try that again. The 60-degree reference angle in quadrant 3, in quadrant 1 would be pi over 3, and in quadrant 4 would be 5 pi over 3. You need to plug both of those values in for theta here and figure out what you get for r. again, I would just use the first equation here. So you are plugging in pi over 3, you get out a 1/2. You're plugging in a 5 pi over 3, you get out a 1/2. So here are my 2 points of intersection. 1/2 is what r is when theta is pi over 3. When theta is 5 pi over 3, r is also equal to 1/2. Now, one quick thing that I do want to show you, just in case your trig instructor never explained this to you. In quadrant 1, for your special right angles, all of them are just going to be pi over 3, 4, or 6. In quadrant 2, they are going to be a improper fraction with the numerator 1 less than the denominator. So 2 pi over 3, or 3 pi over 4, or 5 pi over 6. Now again, these are only your special right triangle angle measures. In quadrant 3, you are going to have an improper fraction with the numerator 1 more than the denominator. So 4 pi over 3, 5 pi over 4, or 7 pi over 6. In quadrant 4, your angles work like this, and in my trig class I actually name whoever figures out the pattern here in quadrant 4 first. I say that we're using that person's name rule. So for right now, let's see, let me make up a name. So whose name is this going to be? We'll just call this Melissa's rule. So you need to double your denominator. That's 6. Subtract 1 from it. So 5 pi over 3. Double your denominator. That's 8. Subtract 1. So that's 7 pi over 4. Double your denominator. That's 12. Subtract 1. So that's 11 pi over 6. So hopefully that will help you guys when you are trying to figure out the points of intersection, because like I said, your calculator is only going to give you that value. It's not going to give you this one. Let's look up at our picture right here. So we are intersecting right here at 1/2 comma pi over 3, and we are intersecting right here at 1/2 comma 5 pi over 3. You'll need to be able to figure out those points of intersection and plot them to help you do section 11.5. So this ends our video on the second part of graphing polar equations.